landing, for instance. The goal in the safe learning formulation, at least the typical safe learning formulation, is to ensure safety during the learning process. So as the robot updates its policy as it learns, how can we ensure that it doesn't violate any safety constraints like crashing into the ground or any obstacles? And there have been a number of different approaches to tackle this problem of safe learning. For example, sorry, it says the meeting is being recorded. Hold on. I think I lost my mouse. Okay, good. Yeah, so there have been a number of different approaches to tackle this problem of safe learning. For example, based on Hamilton Jacobi reachability theory, robust MPC, Gaussian process regression, and also techniques based on formal methods. So what I want to highlight is that typically in the safe learning formulation, the goal is to ensure safety during the training process. So as the robot is updating its policy, and typically in this formulation, the environment that the robot is operating in is assumed to remain fixed. So the obstacle locations, for example, are assumed to stay the same. The thing that's changing is the control policy, so the behavior of the robot. And what I want to talk about today is somewhat complementary. So not safety during the training or learning process, but rather safety during deployment or testing in new environments beyond your training data set. So this is the problem of generalization. So here's a quick kind of formal problem statement just to make things concrete. So imagine that your robotic system has some dynamics. X is the state, U is the control input, and E is the environment that your robot is operating in. So I'm going to use the word environment pretty broadly here to refer to factors that are external to the robot. So if you're thinking about UAV navigation, think about the building that the UAV is navigating. If you're thinking about object manipulation, think about the object that the robot is manipulating as corresponding to the environment. The main assumption that I'll make, at least for now, is that there's some true but unknown distribution that I'm going to call D over your environments that the robot will encounter. So of course, this distribution could be extremely complicated. So the distribution over all objects or the distribution over all buildings. We're just going to assume that there exists such a distribution. And that we have some finite training data set that's drawn from this underlying unknown distribution. So I'll relax this assumption later, but at least for now, this is the main assumption we're going to work with. So your robot then has some sensor. Again, we're focusing on rich sensory inputs. The goal is to learn a control policy that takes in as input your finite kind of training data set, and then basically learns to map observations to control inputs or histories of observations to control inputs. And the goal is to minimize some cost function. So C pi E here is the cost of deploying some policy pi on environment E, maybe over some finite time horizon. And I'm going to assume that the costs are bounded, let's say, between 0 and 1. So you could incorporate things like collision avoidance using such a cost function. So you could assign a cost of 1 if your robot collides with some obstacle, or a cost of 0 if your robot kind of successfully navigates to a goal. But potentially you could also assign costs that are kind of in the middle. And finally, I'll assume that for any policy, we can basically run the policy on our training environments and evaluate the cost that the policy incurs on the finite set of training environments that we're assuming access to. The goal then is to learn some policies. So given this finite training data set of environments, learn a policy pi that minimizes the expected cost across future environments that are drawn from this underlying distribution over environments. And I'll just mention that you can capture, so if you make this cost a binary kind of indicator variable, then you can capture something like value at risk, so the probability of collisions. If you change this objective, modify this objective, you can also incorporate things like the entropic risk. I'll say a little bit more about risk in a bit. The main challenge I want to, again, just emphasize here is that we don't know what this distribution is. So the distribution over all environments, we only have indirect access to it in the form of a finite training data set. So before I talk about our approach, I want to make a kind of philosophical point, which I think is really important, but somewhat underappreciated, which is what do we really mean when we say risk or guarantees or probability in the context of safety critical robotic systems. So when I talk about risk or probability here, what I'm referring to are frequentist style probabilities, so frequentist interpretation. So I want to be able to say, if I run my robot in a million different new environments, in a million different new buildings, then I'm going to see some percentage of collisions, and I want to be able to bound what that percentage is. So in principle, I could run this experiment and compare my guarantee, like whether or not the actual kind of empirical performance on a million different new environments matches my guarantee in this kind of frequentist sense. This is different from what you would get if you had a Bayesian style reasoning. For example, if you used Gaussian process regression, so I think Angie mentioned this as well, depending on what prior you choose, you could end up with very different kind of probability estimates, and they may not correspond to any actual frequentist style bounds. So what I would argue is that when we're talking about safety critical robotic systems in particular, we want to make guarantees that are frequentist in nature. And just to maybe drive home this point a little bit more, the main point here is that Bayesian probabilities are inherently tied to the prior that you use and may not correspond to any actual kind of frequentist bounds. So as an example, think about maybe the simplest possible example, which is just coin tossing. Imagine that there's some biased coin and there's some true but unknown probability of the coin coming up heads. Think of heads as some kind of bad event whose probability that you want to bound. Imagine that you start off with some prior on this bad event. So let's say it's 0.1, so it's a pretty optimistic prior. And then you collect some data set of different coin tosses from this coin. Just for the sake of argument, let's say it's a pretty small data set, maybe 5 or 10 tosses. With a Bayesian approach, so if you just kind of crank through Bayes' rule, you calculate the posterior distribution. What you'll see is a posterior that's somewhere between 0.1 and 0.7. So if you have a small data set, then your posterior is going to be relatively close to your prior. And in particular, it's not going to be larger than 0.7, right? So you don't get a bound on the probability of this bad event, which is heads in this example. This is in contrast with what you would get with the frequentist approach, which gives you a bound, so a confidence interval on the true probability, where the confidence interval kind of holds with high probability over the sampling of your training data set. So potentially this bound, this confidence interval could be very loose. So it could just say that the bound on the probability is somewhere between maybe 0.5 and 0.9. But you would hope that as you collect more data, the bound gets tighter and tighter, but at all points, you actually get a bound on this probability, which you don't get with a Bayesian style approach. At the same time, Bayesian reasoning is a really powerful way to incorporate inductive bias. So if you have some prior knowledge, if you have some domain knowledge, then Bayesian reasoning gives you a really kind of neat way of incorporating that bias incorporating that knowledge into your reasoning system. So one, I think, important question is, can we still provide frequentist style bounds while also being able to incorporate Bayesian style reasoning? And ideally, you would hope that a better inductive bias leads to stronger frequentist guarantees. So in the coin tossing example, if your prior was maybe closer to 0.7, you would hope that you get tighter confidence intervals. So here's the approach we've been taking. So the primary kind of tool we've been thinking about in this context is known as generalization theory. So this comes from theoretical machine learning. And most of this work on generalization theory has been carried out in the context of supervised learning problems, so things like image recognition tasks. The specific framework that we've been exploring is called PAC-Bayes theory. So PAC stands for probably approximately correct. So that's the kind of frequentist part. And there's also a Bayes part there. So as the name suggests, this actually gives you a way of combining Bayesian style reasoning with frequentist style guarantees. And the main idea is then to take this theory that's been developed in the context of supervised learning and basically extend it or translate it into the policy learning setting that I described a few slides ago via a reduction-based approach. The main kind of result of the theory then is an upper bound on the quantity that we care about, so an upper bound on the expected cost that your policy will incur on future environments that are drawn from this underlying distribution over environments. And the algorithmic approach then is to basically find policies that minimize this upper bound, so that give you the best possible guarantee on generalization that you can get. So I'll give a very quick kind of overview of PAC-Bayes theory, just the highlights. I'll first describe it in the context of supervised learning, and then I'll talk about how we can extend it to the policy learning setting. So in the supervised learning setting, let's assume again that we have some unknown distribution D over your inputs. So this is some distribution over all images that your robotic system might encounter. And we're going to assume again that we have some finite training data set. So n examples of images and their corresponding labels that have been drawn from this unknown distribution. So PAC-Bayes applies to learning algorithms that have this following pretty general kind of structure. One important feature of PAC-Bayes is that it works with distributions over hypotheses rather than just kind of deterministic hypotheses. To make things concrete, imagine that you have some neural network architecture that you picked, maybe a CNN or a transformer or something like that. So some particular architecture that's parameterized by some set of weights. So what we're going to do with PAC-Bayes is we're going to first choose some prior distribution P0 over the weights of that network. And then we're going to choose some posterior distribution based on the training data set that we have access to, and potentially also based on the prior that we chose. I'll mention that the posterior doesn't have to be the Bayes posterior. The results I'll mention basically apply to any choice of posterior, not just the Bayes one. So here's the main result from PAC-Bayes. So it says that with high probability over the sampling of your training data set, we can upper bound the quantity that we care about. So we can upper bound the true expected loss of some posterior distribution that we're going to choose as a combination of the training loss, which we can evaluate given our finite training data set, plus a regularization term. So you can think of the second term as a kind of complexity measure, which measures how far away any given posterior is from the prior distribution. So this is saying don't go too far away from your prior in order to minimize the training loss. So if you think about this right-hand side as an objective, this is balancing how well you do on your training data set with how far away you go from your posterior. So this gives us a guarantee on generalization. So this upper bounds the expected loss on future examples that your system might see. So of course, the policy learning settings that we're interested in robotics context are pretty different from the supervised learning setting. The main technical challenge has to do with the non-IID nature of your observations from time step to time step. So at every time step, your robot gets an observation, it chooses some action, that action then influences the future observations that your system will see. However, we did assume that the environments that your robot is operating in, so the buildings, for example, those are drawn IID from some unknown distribution. And basically, that's the main assumption that allows us to apply these PAC-Bayes techniques. So I won't go into the details of how we can extend from supervised learning to policy learning. I'll just give you a sketch for the intuition behind the idea. So again, in the supervised learning setting, we have some input, maybe corresponding to an image. We have a hypothesis that takes the input, maps it to a label, and we have a loss function that tells us how well we did on this example. And then PAC-Bayes, as I kind of outlined earlier, gives us a bound, a guarantee on the expected loss on new input data. What we're going to do is basically map the policy learning setting onto the supervised learning setting by thinking about the environment that the robot operates in as corresponding to the input. The policy then corresponds to the hypothesis. So the policy indirectly maps environments to actions or sequences of actions indirectly through sensor measurements. We have a cost function that tells us how well any given policy does on any given environment. And basically with this mapping, which I've only described informally, you can look at our papers for more details. We can basically extend the PAC-Bayes result to the policy learning setting that we care about here. Here's a sketch of the results. So it basically says that with high probability, so delta is some parameter that you get to choose over the sampling of your training data set. We can upper bound this quantity, which I had said this is the quantity that we're trying to minimize, so the expected cost on future environments that are drawn from this distribution D. We can upper bound that quantity as a combination of the training cost, which we can evaluate given our training environments, plus this kind of same regularization term, which again you can think of as a complexity term that's preventing overfitting. And this bound holds for all choices of P, so all choices of posterior distributions over the weights of your policy network. And so this provides a guarantee on generalization to new environments. And basically the algorithmic approach then is to find some posterior distribution, so some posterior distribution over your policy space that minimizes this upper bound. So that gives you the best possible guarantee that you can get. So the algorithmic kind of approach then is to choose some prior distribution, P0, over the weights of some neural network policy whose architecture you choose. And then we choose some posterior distribution, maybe using Gaussian, let's say, over the weights of your network in order to minimize this upper bound that we get from PAC-Bayes. And you can do that using many techniques, so stochastic gradient descent, black box optimization techniques, or even reinforcement learning techniques. So at the end of this process, basically we end up with two things. So the first is a posterior distribution over the weights of your policy network, which you can then sample from when you want to deploy your policies on future environments. And then we also get a certificate on generalization. So this upper bound on the expected performance of your posterior distribution on future environments. So let me talk about some results that we can obtain with this methodology. So the first example I'll consider is this drone navigation example that I've been using as a kind of running example. We're using a parrot swing drone, which is a hybrid between a fixed wing and a quad rotor, so it takes off vertically, but then transitions to forward flight. And in this example, we're using depth images as our main kind of sensing modality. The drone itself is too light to have a real depth sensor. So what we're doing is simulating depth images from the perspective of the drone, but using off-board cameras. So the only information that the policy has access to is a simulated depth image simulated from the point of view of the drone. So this is kind of an example of what a depth image looks like. We're then training a neural network policy with a particular architecture, really a distribution over policies to optimize the PAC-Bayes bound. And basically what the neural network does is it takes in as input the depth image or a sequence of depth images, and it maps it to some motion primitive. So we have a pre-computed library of different motion primitives, things like fly straight, turn left, bank right, and so on. So the neural net is responsible for mapping the sensor observations to choices of actions. This is trained purely in simulation using some finite number of training environments, and then we deploy it on the actual hardware system. For this example, we used 1,000 different training environments. Again, we optimized the PAC-Bayes bound to get our policy distribution. The bound that we get from PAC-Bayes is 93% on the success rate, so 7% collision rate. So success here just means going to the end of the room without colliding with obstacles. And the empirical success, so we ran this policy on many different environments, and the empirical success is around 93.3%. So we see that the bound that we're getting with PAC-Bayes actually translates to the real hardware system, even when we have these rich sensory inputs and neural network-based control policies. So I'll just play some videos of a few representative kind of trials on the system. That one was a crash, so it's good to show the failures too. All right, so we've also implemented this on different application domains, specifically in robotic manipulation. So this is a Franca Panda arm with a RGBD camera on top. In this case, we trained a prior distribution again over some neural network weights using human demonstrations. This is imitation learning to choose the prior. We then have some data set of additional objects that we use to train the posterior distribution over policies by optimizing the PAC-Bayes bound. Again, this was trained in simulation using a certain set of objects, mugs in particular, and then we deploy the learned policy that we get from PAC-Bayes on new environments, new mugs that were unseen during the training phase. Again, the bound on performance, the bound on the success rate that we get on this example is around 93%. The prior, which again is just based on imitation data, achieves a 83.3% success rate in simulation if you just exhaustively test it on many different objects. And the posterior, which we get from PAC-Bayes, is around a 98% success rate. And then if you look at the hardware trials, these are 3 different random seeds. We see that the bound we obtained using PAC-Bayes, again, are actually validated on the real hardware system. We've also implemented this on more kind of complex navigation tasks. So this is a quadruped robot, the Ghost Spirit robot, that has a RGB camera attached to it. So this is the first-person RGB image that the robot is using. So that's the only sensor information that the policy is using. And the goal here is to basically navigate to this goal location that you see marked with tape. And these are indoor environments that were not seen during the training phase. Skip a little bit. Yeah, so we tested these on many different environments. So this was trained in simulation using a data set, again, a finite data set of different environments. And then we obtained a PAC-Bayes bound of around 70%, and then a success rate of 78 or 77%, depending on whether you apply this in simulation or hardware. Okay, so far I've assumed that there's this kind of true unknown distribution over environments. But what happens when you have distribution shift? And I think there's 2 questions here that one could address. So the first one is, can you detect when your robot is operating out of distribution? So when your robot is being deployed in some environments that are drawn from a different distribution. In this case, the robot could potentially act more conservatively or cease its operations altogether. And the second question is, can we learn policies that are robust to distribution shift? So I'll quickly talk about both of these. So again, if we think about the drone as an example, if we train without any wind, but then we deploy the system in environments that have wind, can we detect that there's been this distribution shift? And ideally, we want this kind of OOD detection to have 2 properties. So the first is we want some guaranteed confidence bounds, so bounds on the false positive and false negative rates of detection. And the second point I want to make is that we want our auto distribution detection to be task relevant. So if there's some portion of the environment here that changes but doesn't have any impact on the robot's performance, then in some sense we don't really care that there's been a distribution shift because it doesn't impact the performance. So the approach that we've explored is to train a policy using these PAC-Bayes techniques that comes with a guaranteed bound on the expected performance under the training distribution. If we then observe that there's a violation of that bound, then that gives us high confidence that we're being deployed in auto-distribution environments. So if you think of the cost as corresponding to the distance to the closest obstacle, then we have an expected distance to the closest obstacle. And then if we see that bound is being violated at test time, then we can say with high confidence that we're operating out of distribution. So this is a video again of the drone example where we trained without any wind, and then we deploy the system with varying amounts of wind gusts. So there's a fan at the bottom left of the picture, and the wind goes from around 0 to 5 meters per second. And basically what you'll see is as the wind increases, so as the robot um, sees more wind going from 0 to 5 meters per second, it gets closer and closer to the obstacle. And that's basically the signal that it's using to know that it's operating out of distribution. So here's a plot that shows that. So the x-axis is the percentage of the max wind, and the y-axis is the confidence that the robot has on it being out of distribution. All right, so I'll just wrap up with a final point, which is about learning distributionally robust policies. So not just doing detection, but actually designing policies that will work well out of distribution. So in this context, what we want is to learn a policy that is robust, not just to new environments from the training distribution, but actually to new environments from some different distribution. One answer to this question of distributional robustness is to use risk metrics. So for example, if you use the entropic risk, so the exponential risk, that provably gives you a bound on the expected performance on future distributions and new distributions that are within some KL ball around the training distribution. But the challenge here is that the KL divergence doesn't necessarily have a physical kind of meaningful interpretation. So one example is if during training time, you only see red objects. During test time, you see blue objects. Oops, in this case, the KL divergence is gigantic. In fact, it's infinite because you've never seen blue objects in your training distribution. So somehow you need some kind of task relevant representation of your environments to meaningfully quantify distribution shift. And the specific approach we've been exploring is to use the Wasserstein distributionally robust optimization framework, which I won't go into the details of in the interest of time. So we've implemented this on a manipulation example where we trained using a certain distribution over objects, and then we test using different objects that were not seen during the training phase. And then we compared our policies to other techniques like domain randomization, for instance. All right, so let me just skip here. I know I'm pretty much out of time. So this is our group. So we have 8 PhD students. A number of the students are here. So Alec is here, Vince is here, David, I think, will be here, and Sasha will be here as well. So I'll leave you with this conclusion slide and take any questions you have. Thank you.
Really wonderful talk. Thank you. How does the PAC-Bayes theory deal with settings with few numbers of samples?
Yeah, that's a good question. So part of the trick to getting relatively strong bounds is to choose a good prior. So I guess I see that as kind of an opportunity. So if you have some domain knowledge about your system, so if you know, for instance, something about the kinds of environments your robot might encounter, maybe you can come up with a synthetic distribution over environments. You can use that to inform some prior. In that case, you might only need a relatively small number of real-world environments to get reasonably strong bounds. So that's one approach we've kind of played around with, like different ways of choosing a prior, either based on kind of inaccurate generative models or using imitation learning, where someone gives you a policy that's maybe not perfect, but good enough to get a prior. And then you can fine-tune that using a relatively small number of new examples. At the same time, though, I mean, I think to get really tight bounds, you still do need many more like environments. In these examples, we were getting bounds kind of in the 90s with something on the order of 1,000 different training environments. So that's roughly what we can get with these techniques, at least for right now.
Okay, thank you.
I think we can maybe take 2 more questions. I don't know if yeah.
So thank you for the great talk. My question is, how limiting is it that your cost function needs to be bounded between 0 and 1? Because you might have some costs that you incur over time, right? Like a violation that you repeat over several time steps, or we can come up with other examples.
Yeah, that's a good question. So the main assumption here is really boundedness. So not so much bounded between 0 and 1, because you can of course always rescale. There are versions of the PAC-Bayes bound that relax that assumption. So they work for unbounded costs. We haven't, I think, personally, tried them out, but they do exist, and in principle, you could replace the bounds we're using with those ones. So I don't think it's a huge kind of technical barrier.
Thank you so much for the talk. Could you just provide some intuition regarding how delta can be used as a tuning knob? Because as per my understanding, it affects only the regularizer term.
Yeah.
So how does like changing delta change the conservativeness or aggressiveness?
Yeah, good. So the physical meaning of the delta parameter is that, so the PAC-Bayes bound says that with probability 1 minus delta over the sampling of your training data set, that upper bound of the expected cost on future environments holds. So typically we choose delta to be something like 0.01. So with 99% probability over the sampling of your training data set, we can upper bound the expected cost. So maybe if I just go back quickly to the slide. So as you said, it shows up just in this regularization term. So as you decrease delta, the regularizer weight kind of increases. So it says pay more attention to your regularizer if you want really, really high confidence. So that's kind of how you can use it as a tuning parameter. So the intuition is that you could get really unlucky in your training data set. So the extreme cases, if you see the same example over and over again, then there's really nothing you can learn, even if you have many examples. So that's basically like what this delta is controlling. So it says if like potentially you could get really unlucky, but most of the time you'll have some data set that you can then learn from, and then this bound is going to be well.
Yes, so my question was related to the hardware experiments. You said that you couldn't get an RGBD camera on the actual parrot. What is the image that's being sent, and is it being updated as it's flying, or is this a one-time it views and then makes the decision?
Yeah, good. So yeah, this specific drone is like is pretty light. So we did try. We tried to get some cameras on there, but we had a hard time doing that. So what's being fed to the policy is a simulated depth image. So we have a Vicon motion capture system here that knows the locations and the geometries of the obstacle and the location and the orientation of the drone. So you're using that information to simulate what the drone would see if it did have a depth camera. And that's the only information that the policy is using. So we're kind of cheating in some sense by using the external camera, but we're only using, the policy is only using the simulated camera as if it was from an onboard camera.
But is it testing the policy from all of you showed in the next slide, the multiple trajectories that's placed? Is that something that it's calculating and using the sensory information from what all of those would be?
Oh, I see. No, it's not using that. It's not using that. Yeah. So it's only using the depth image, and then basically we have a neural net that takes the depth image and maps it to a selection of one of those motion images. Yeah. So it's a pretty simple kind of architecture.
Okay, so thank you again for this really interesting talk. And could maybe the speakers for the second round of lightning talks come up? Also, we have a panel discussion later. So if you have like more questions, you can also, ask them later on during the panel. So it will be open for everybody.